How's it going, everybody? And I'd like to welcome you to our next video where we discuss a topic that when I was going through and putting this particular section together, I had to think about how I was going to actually put it together, because based on, and the nice thing about it is that Cisco kind of gives us a blueprint, no pun intended, on what to look for and how to actually put this together. So when I was looking at this, my pen, where's my pen? My pen is not working. Okay, fix that. As I was putting this together, I came to the realization of how do you break this down? Because Unicast Flooding and some other things, as we'll go through here, they're not complicated topics, but if you don't understand how devices actually operate, it can be difficult to figure out where exactly the problem is if you don't understand the underlying architecture of what the device does. So I'm over here on the switch, and as we're going to go through here and talk about Unicast Flooding, and we talk about, what's the other one we have down here? We're going to talk about asymmetric routing, out of order packets, and what's the other one? Impact of Microburst. So we're going to cover these topics in this video and how each one affects the network on an individual basis. So what Unicast Flooding is, and this diagram actually gives you a very good representation, and this is taken actually right out of Cisco's documentation. So if you were to go look up Unicast Flooding and look up the Cisco docs, you would actually see this. So we have PCA here is trying to send to PCD. Now the benefit is they are both on the same switch, they're both in the same subnet. Now you can disregard the fact that it's a Cat 2950 because of the fact that that does not make a difference. Any modern Catalyst switch is automatically going to be doing what they call transparent bridging. Transparent bridging is when you take one host and you're able to send to another host, and the intermediary device in between them, so the switch in this case, is never seen. These guys appear as they're directly connected. There's a difference between that and translational bridging, which is you got this and it goes to a router, maybe, say R1. This goes to another router, and then this goes to a switch. So anybody here, it would actually look like they're two different networks because the router is translating. Maybe it's doing some sort of bridging or something to that effect. But that's a video for a topic for another video. But Unicast Flooding, usually that happens when you have a situation where, let me draw a switch here. You have a switch and you have a variety of users plugged into it. So we'll have a bunch of people plugged into this switch and over here, because you can't use both sides of a switch, or all four sides. So you have, usually you can only use one. So that's even a little off. But anyway, so we have all of these connections to the switch. If the destination MAC address for a sending device is not known, that's when Unicast Flooding occurs. So what ends up happening is, if the destination MAC is unknown, so UNK is unknown, what ends up happening is the switch receives a packet, or the frame, in, and this goes with routing as well. It'll actually do this too. And I'll talk about that more in detail later. The switch will receive that frame in. The reason I say frame is because frames are at layer 2 and a switch is layer 2. It receives that frame in, and if it doesn't know what to do with it, it'll send it out every interface that it's got connected to it, including maybe a trunk port to another switch. So let's assume up here this is switch 1, this is switch 2. So we have a frame that comes in, the destination MAC address is unknown. So the switch doesn't know what to do with it, so it sends it out every port that it receives it on, except for the one that it sends it out every port except for the one it receives it on. So by doing that, it's able to say, hey, do you know about XYZ? So it sends up to this, across the trunk even, up to switch 2, and then switch 2 will respond if it knows how to get there. And what actually ends up happening, let's assume that, this is switch 2, then we have switch 3, and we have switch 4, so on and so forth. You have all these switches connected together, and switch 2 will send up to switch 3, and switch 4 until it reaches an endpoint where there's nothing else left to do. This usually only takes a couple of seconds at the very most. I mean, you might lose a ping or a ping or two when you're going through. So instead of getting the dot exclamation exclamation exclamation, you might go dot 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 exclamation exclamation. And anytime you get an exclamation, that means somebody responded to you. So if you get dot 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 exclamation point and you were to do it again, you're supposed to get 5 good ones after that, or whatever the repeat rate was. So unicast flooding is when the layer 2 address you're trying to send to is not known. So if it knows about it, it will go ahead and forward it to it. Now, here's one of the things that I find people, especially when they're coming into the CCNA, they have a hard time grasping the concept of this. What they end up seeing is you have, let's say you have a switch here, and you have a switch here. And these guys are connected down to maybe this is your access layer. And we have a distribution switch. And this guy is connected to a router. Alright, so we have R1, we have a distribution switch. And this router is acting as a router on a stick. So it's doing inter-VLAN routing. So what ends up happening is, if host B wants to send to host A, what it's going to end up happening, and let's assume for a second that this is the 10.1.1.0 and this is the 10.1.2.0 subnets. What's going to end up happening is host B is on a different subnet than host A. So what's going to end up happening is this guy is going to send a frame to here, because the source MAC address is going to be here. The destination MAC address is going to be whatever sub-interface MAC address is assigned by the router to the sub-interface of the router's interface that's providing the transit between the distribution switch and the router. So in this case, it might be fast 0/0 is the actual physical interface, but you might have .1 and .2 are going to be the sub-interfaces for VLAN 1 and VLAN 2. So the sub-interface of VLAN 1, this will be the destination MAC. So what's going to end up happening is the host B is going to put his source and router 1's destination. And then what's going to end up happening is the router is going to do what I talked about in the previous video when it comes to Ceph. He's going to take that layer 2 information and he's going to rip it off. He's going to use the routing table to look up the next hop. So what interface do I have to figure out? What interface does this packet go to? And then use a switching process, whether it's process, fast, or Ceph switched to the outgoing interface. Then I'm going to rebuild the layer 2 information. So the source is now going to be the router. The destination is going to be host A's MAC address. So that's how the translation goes between a router on a router for when it comes to routing between subnets. Now, let's bring this down here just a bit. So, like I said, if you would like, I can send you this OneNote video or OneNote file. It's not too big, and it'll have all this information already in it. So this is just a very large example of how Unicast flooding works in spanning tree. So now that we've talked about Unicast flooding, let's talk about out of order packets and how that can affect you. So out of order packets is the delivery of packets in a different order from which they were sent. Out of order packet delivery can cause packets to follow multiple paths or via parallel processing paths. And what ends up happening, so that's the definition, if you will. So we have, let's draw it out like this. We have a switch, we have a switch, we have a switch, and then we have another switch, and then we have a router. So these guys are all connected to each other, and everything's all hunky-dory. So what ends up happening is, you could have, and let's assume just for a second that we have a connection going this way, we have a connection going this way. These are all equal cost routes to everywhere we're going to go. There's 2 routers, and this guy connects down to this guy, and there's another switch that these guys connect to, and this is the destination. So we'll put this is the destination, and we have a sender here. And we have a destination here. So what ends up happening is when you have out of order packets, and this is a specific, especially harmful, I guess would be the best way to put it, when it comes to voice over IP. So voice over IP. The reason for that is because of the fact that the way the packets are delivered. Now, with voice over IP, this is a UDP transmission. Now, I notice you see up here, TCP, one of the things it has is the ability to prevent out-of-order packets, and that's what they use the sequence and the ACK, or the SYN and the ACK. And what this basically does is it allows you to send packets out of order, and the router, as it receives them, will buffer them inside of the input queue, or the inbound queue on the inbound interface. It will reorder them before it begins to deliver them. This happens extremely quickly, but it still needs to be done because the fact of the matter is, if it delivers them out of order, your ouch could show up as ow. And you'll be like, what? So, if you deliver out-of-order packets, or along the path, something gets dropped. So, you're trying to say A, B, C, D, E, F, G, and let's say that C and F get dropped. So all you hear is A, B, D, E, G. And you're like, okay. So, what was meant to be sent is C and A, B, C, D, E, F, G, which makes sense. If you speak English, that's going to be letters in the English language. But if packets drop, so C is not there anymore, F is not there anymore, all you get is A, B, D, E, G, that's not going to make a lot of sense to you. You know someone's probably saying the alphabet, but you're dropping packets. So that's going to be a bad thing. So what ends up happening, if it's a TCP connection, what will end up happening is that whole section, that whole transmission that we have here, this entire loaf of bread that I just drew, but I'm not an artist, by the way, that entire section of data will be resent because you'll have packet loss. Now, with UDP, it's best effort. It doesn't matter. If nothing gets there, there's no checking to see if it did. So that's why voice is such a dynamic protocol, and sometimes it can be difficult to deal with because of the fact that you may not realize what's going on until it's too late. Or there could be some sort of latency on the network, or some sort of degradation that you can hear echo, or you can hear yourself talking, or whatever the case may be. But I'm not a voice guy by trade, but I've dealt with it enough to know, how some things are supposed to work. But out of order packets, they're going to take the same path. So this guy does this, goes here, he goes this guy, and this guy takes this path. For whatever reason, he goes this way. So they both go to the same end station, but they take different paths to get there. Now what's going to end up happening is, and in case you, just for a second here, we're going to bond these two together, and we're going to make these all equal cost routes. They're going to be 10, 10, 10, and 10. So that they're all equal cost routes. So what ends up happening is the routing process is automatically going to load balance across all redundant paths. So you're going to receive packets in on this interface, and at this point you got traffic coming in, and you need to figure out a way to get the out of order packets back into order. So one of the functions of TCP is to prevent out of order delivery, either by reassembling the packets in order or forcing retries of out of order packets. So if you have an out of order packet, it's going to the receiver is going to signal the sender to resend. Okay, so there's going to be a TCP flag tripped, sent back across the wire for the ACK, and say, hey buddy, I didn't get this, resend that entire transmission. So this is typically what happens when you get the windowing size drops. So you might be at like 200,000 for your window size, and then all of a sudden you drop down to 50,000. And you're like, well, why did it drop? And then you do some packet captures and you realize that there's a lot of retransmissions. So you start looking at it, and it could be a latency issue, it could be bandwidth is being improperly assigned to different applications incorrectly, things like that. So depending on the situation, that could happen. If it does happen, you at least have an idea as to what's going on. So I'm going to pause the video for a second, and then when I come back, we're going to look at asymmetric routing for a moment. So asymmetric routing, as it's called, is basically this. Bring this down here. And this is actually a very good instance of how asymmetric routing goes. So you have the sender and you have the receiver. Okay, so as you can see, packets come out this way, go up to here, and then they come back on a different response path. Okay, so that's not necessarily a bad thing, but asymmetric routing, depending on the situation, could cause issues. So, and let me bring this up here. This is actually a really good article that I read, and when I read it, I was like, "Oh, this is good." And I like the way it's put. It's a fancy way of saying packets are using different paths according to the direction of the traffic. If everything works as expected, you might not even realize it. This is happening. So, imagine you had a ticket. You had a ticket on the lab involving ASR. Oh, they're talking about. Traceroute is going to be the most. I'm reading as I'm watching this. So yeah, he does point out that you probably think traceroute, but a regular traceroute only gives you the path used to reach the host, not the path on that way back. You can actually change this up. What you can do is you can do a traceroute. And we'll get into this a little more in detail when we get to IP options and the some of the options that are out there. You can actually do traceroute and hit enter, and what you can do is you can actually record the traffic out and then back. And what that'll do is it'll tell you every IP on the way out there and every IP and the time it took for each hop on the way back in. So that'll give you a to and from way of looking at how things are working. So it gives you a lot of flexibility when you're trying to troubleshoot why something is working. Now, when an internet module receives or routes a datagram, it checks to see if the record route option is present. Record option is present. If it is, it inserts its own internet address as known in the environment into which the datagram is being forwarded into the recorded route, beginning at the byte indicated by the pointer. Fancy way of saying, I think that's right out of the RFC though. Yeah, that's why it's written so technically. What ends up happening is if you do a record route, you're going to get the this was the R1, R to R3 to R4, R4, back to R2 to R1. So as you can see, it follows this path to get to where it needs to go. That's fine. I mean, it's not going to break all routing designs, but it definitely could prevent some things from happening. So the idea behind asymmetric routing is when you have traffic come in one way and leave another, that could break designs. So you might have a situation where you have an application that is port aware, so whether it's got its own designated port, or you may have done some sort of policy routing to where all traffic does this. But if you have some sort of stateful firewall or stateful packet filtering and traffic goes out but comes in a different way, it could be dropped. So especially when you're dealing with anything that's using stateful. Now, I'm going to go on a limb here, and I know this for a fact that this works because you can use asymmetric routing even with firewalls and they will work. But if you have a stateful firewall, and what will end up happening is there's going to be a state table with a bunch of information inside of it. So you're going to have the source. So this is going to be traffic that is originated from inside of the network. And then you're going to have the outside world. Okay. What ends up happening is a state table takes records the in to out information on that route. It records it, and if that information does not match coming back in, so if the source and destination information of the returning packet differs from anything in the state table, it could be dropped. So that's where dealing with a stateful firewall or stateful routing comes into play. If you're dealing with anything like that, that could hinder you. So it's important to try to keep traffic flowing out and coming back in the same path. If it's possible, go ahead and do it. The way you can do that is, in this example here, what they did was they actually went in on the R4 and they configured a static route and said anything that comes in goes this direction. Well, you can change that, but what you could do on all of these links, and this is always going to be on this interface and this interface, is you're going to change the metric to make this route look better than this route. So it's always going to be the receiving side. Now, when the router does a calculation, it does it on its physical interfaces. So it takes whatever it knows about and does a calculation. You can manipulate traffic, BGP with the MED, you can tell. Let's assume this is Autonomous System 2 and this is Autonomous System 4. You can use Autonomous System 2 to try to influence Autonomous System 4 how our AS4 will route traffic to AS2. It's called the multi-exit discriminator. You can actually modify that to try to influence another autonomous system's routing. It's not usually ever. I've never seen it successful. Usually, we use local preference, or we use some sort of. In most cases, you use a community. You'll use just a normal community, and you'll send it out there and try to modify the local preference for a particular route. But depends on the situation. Now, on your local interface, you can make one route look better than the other. So you can give one a really bad delay, and you can make traffic all go this way. So there's different ways to traffic engineer your network. It's just a matter of determining how you need to do that. So when we get into more of the routing issues that you could potentially run into, we'll talk about that in much more detail. But the idea behind this is to make sure that traffic routes the correct way all the time. And this is actually the fix. So if you have asymmetric routing where traffic is doing this all the time, if you were to put a static route in here and say anything that comes in is going to get routed back this direction, that will actually facilitate this type of routing where it'll come in from R2 or from R3 to R4 and then back again, the correct path. So that's the idea about having a single path, but then over here you notice that these guys aren't getting utilized. So you can actually go in and tweak the metrics however you need to get this type of routing to work. So playing off of his example, let's say you do have a ticket in the lab that says R1 is sending traffic to R4, but when R4 sends traffic back to R1, it's using a different path. Make sure that all traffic traverses router 1, router 3, router 4 on traffic transiting between R1 and R4. So it's a pretty straightforward what they're telling you is telling you that there's asymmetric routing going on, and you have to go in there and fix that. Whether it's modifying a metric to make something worse, or you have to go in and put a static route, unless they tell you don't use a default route. If they tell you don't use a static route, you're not. Technically, this is not a static route. It's the same syntax, but it's actually a default route. Default route means if I don't know what else to do with it, I'm going to send it out this way. Technically, it's still a static route config, but you might be able to get away with it. I'm not going to ever do that in the lab. I want to make sure I play it as safe as I can, because you never know what's actually going to happen. So, but that gives you an idea of what asymmetric routing is and how it can actually affect what goes on in the network. So the next one we're going to talk about is just a little bit of a background on the record. Now this right here goes into a little bit of detail. It says, in case you were wondering about why the number of hops is a maximum of 9, this is because of the limitation of size of the IP options. You have a maximum of 40 bytes. So what basically that means is you have 32 bits in a IPv4 address, right? So 32 bits, this equals how many bytes? 4. Okay, so that's going to be the originating IP. So that's going to take up 4 bytes out of the gate. So you can add up to. So we're going to take 4 times 9 is going to be 36. So you can have up to 4 times 9 equals. So you can have up to 9 records inside of your trace route to respond with. Anything higher than that, you're going to be using up more space than what the IP address header has. Because of the limited space in the header, only 9 addresses at most can be stored, and even fewer if the header contains other options. So at the most, you're going to be able to get 9. So therefore, the packet arrives with the first 9 addresses stored in the option. The receiver has no way of knowing what routers were used after that. So let's assume you've got 15, 10, 11, 12, 13, and 14, and 15 may not be recorded. So just because of the fact that you run out of space in the header to record things. Now this is an IPv4 header. If you were to use an IPv or a trace route for IPv6, I believe the 60 bytes is the header length. So, but when we get into more of that, we'll talk about that when we get into IP options and stuff like that. But that's just a basic overview for you as to how things would actually work. So the last thing we're going to talk about in this video is going to be the impact of microburst and what microburst is. Microbursting is a behavior seen on fast packet switch networks where rapid bursts of data packets are sent in quick succession, leading to periods of full line rate transmission that can overflow packet buffers of the network stack, both in network endpoints and routers and switches inside the network. It can be mitigated by the network scheduler. In particular, microbursting is often caused by the use of TCP protocols on such a network. What microbursting is you have a router that's trying to send traffic to two other routers, and what ends up happening is this guy, when he's trying to send traffic, he looks at his packet buffers and says, I don't see any latency, I don't see anything in my packet buffers, so I'm going to go ahead and I'm just going to start sending it. Now, what line rate means is that this is a 100 meg or even a gig connection, 100 meg per second. What's going to end up happening is the router, if it's capable of forwarding at gig rate, it will send a gigabit's worth of data for that second out that interface. Now, if that includes all the packets data that it needs to send in bits, then for that 1 second, the router was sending a full line rate. So line rate means you're going to utilize every bit of bandwidth that's capable of being on that interface. So there are some issues where that can come into play, and you could get a spike on the that you might get packet drops and things like that. This is typically caused when going from an idle period of time in the network where there's not a whole lot going on, and all of a sudden you get a mad rush of an FTP session starts up. This is typical when you start sending like an FTP session, where what will end up happening is you'll see your bandwidth shoot up to say 3.4 meg or 4.3 meg, and then eventually you start seeing it taper off, and you might get down to a steady windowed session of say 2.1 meg per second, and that stays pretty fluid because you're not overloading the circuit as traffic is flowing across it. But what you are doing is you're providing a smooth, steady flow of traffic through the network, and if other traffic wants to come across, it won't be hampered or hindered by a large amount of data being sent across the network. So that's just one of the impacts of microburst. I will try to simulate what that looks like in coming up in the other demonstrations that I do. But that's the basic idea of what microbursting does and how it actually works. So if you have any questions, feel free to drop me a line on my YouTube channel. Other than that, I hope this has been informative for you. I want to thank you for viewing.